So the first bound that I want to show is the upper bound on the right side. So the probability that the last crash happens after a certain time after n, that probability is small, that it's going to 0 as alpha goes to infinity. So the reason why this walk is kind of hard to study is because, of course, the parameter is increasing. If the parameter was fixed, 1 plus epsilon or 1 minus epsilon, then this would be easier. This would be the exact same thing as the Poisson branching process, except we're resetting to 1, and we actually know a lot of stuff about that. So the approach that we're going to have to studying this one with the increasing parameter is to compare it with different ones with fixed parameter. So if we take certain intervals and the time, we can make a smaller process in that interval by fixing the parameter in the beginning of the interval. And if we want a bigger process, then we can fix the parameter at the right end point of the interval. And the actual process will be somewhere in between there, so we can use that to make bounds. In this case, we're taking a smaller process starting someplace before the place that we're actually interested in. Over there is n plus alpha n to the 2/3. We're interested in an upper bound on the last crash happening after that. So in order to do that, let's look a little bit behind at n plus lambda n to the 2/3, where lambda could be anything. It could possibly just be alpha over 2 or something like that. But we're going to see later that there is an optimal value just to get the best possible upper bound. But anything you use gives some upper bound. So we want a smaller process here. So we start by taking the height at n plus lambda. Wherever it was, we bring it down to 1, so that makes it smaller. And then we hold the parameter at this point to 1 plus epsilon, where epsilon is lambda n to the minus 1/3. So from here on, the smaller process is not going to change its parameter anymore, and the original one is changing. So over there, after alpha, since one is bigger than the other, if the bigger one has a crash, the smaller one has a crash as well because it gets squeezed under there. So let's look at the probability that the last crash of the smaller process is over there. So since we put the height to 1 here, we can pretend that this is actually where we start. We can forget about everything before. And for the fixed parameter process, the scale of the size of the walks is going to be like epsilon to the minus 2. So that's what we're going to be using. We want this, well, the last crash to be after beta epsilon to the minus 2. And since beta epsilon to the minus 2 has to be this interval from lambda to alpha, then beta has to be alpha lambda squared minus lambda cubed. And we're going to use that later to find the optimum value of lambda. So how do we find an upper bound for the probability that the last crash of the fixed parameter process is bigger than that? So the fixed parameter process is going to have some number of crashes, and then it's going to go to infinity. Because since this is the 1 plus epsilon process, there is a positive probability that it goes to infinity. It's a small probability. It's actually in the order of 2 epsilon. So that's very small, but if you try enough times, then it happens with probability 1. So the first thing that we say is the number of crashes, and C can be any number, and then given that it was that number, what is the probability that the total of the size of all those walks is bigger than K? This K is beta epsilon to the minus 2. So, but we want the sizes of those walks conditioned on the fact that they are finite, because we already chose the number of crashes, right? And luckily there is a very simple looking exact formula for that, which is the same as it would be for the parameter for the Poisson branching process with parameter 1 minus epsilon. So that's easier to study because it never goes to infinity. And then we do some more calculations and changes of variables. These things become integrals, and there is an answer, a very nice looking answer, which repeat there. So we want this bound to be as small as possible, and that function is decreasing in beta, so we want to maximize beta, and that happens when lambda is 2/3 alpha. So that is in this picture here what we use. We start from 2/3 alpha and go up to alpha. Then we just plug the numbers in, and there is our first bound. It looks like e to the minus alpha cubed, and although I'm not going to show those here today, all the other bounds actually also are in that scale of e to the minus alpha cubed, which is very nice. So this is the second bound that I want to show. It's the lower bound on the left side. Again, it's a very similar thing. We look a little bit before the place where we're actually interested in. This time we call it n minus gamma n to the 2/3. Bring the height down to 1 and stop the parameter for the smaller process here while letting the parameter for the original process keep growing. So in this case, we want no crashes after n minus alpha to the n to the 2/3. So the thing is that if the smaller process doesn't crash, then the bigger process can't crash either. So let's just look for a lower bound on the probability that the last crash of the smaller process is inside this interval. So it's not over there. And the way that we're going to do that is that we're going to consider all the walks that start inside this interval for the smaller process, because it can't crash many times here. That's okay, I just don't want it to crash over there. So out of all the walks that start in this interval, I'm going to call them success if it goes to infinity, because then we're done and there is no more crash after the end of the interval. And I'm going to call it a failure if it crashes again, but if it crashes after a long time, like on that first picture, that is a failure. A long time, we say it's a b n to the 2/3 for some value of b, which can be optimized again to find the best possible bound, but really almost any number you use will work. But also, if the walk crashes in a smaller time than that, I'm going to call it small. And the reason why small is not a failure, even though it's not a success either, it's because it doesn't take up much of the interval, so you can try again. And what's going to happen is that the probability of some walk being not small, so that it even has a chance of being a success, the probability that that happens is very small. It's actually in the order of n to the minus 1/3. So it's going to 0 as n goes to infinity. So it's a small probability, but if you try enough times, then you have a good chance of that happening at least once. In fact, it can only happen once, right? Because if it goes to infinity, then you don't try again. But so small walks are not that bad because you get to try again. The big walks that are finite are bad because then the interval just became a lot smaller and you have fewer chances of trying again and succeeding.